There's still one big missing piece from all of this, and that is we've been assuming there are no indexes. And sometimes there aren't, and you just have to do the full nested loop join. But what if there was an index on one of the columns involved in the join condition? So I've got this same join we've been looking at, games join events, and the condition is where the EIDs match. So what if there was an index on either this column in the games table or this column in the events table? Then which one of those relations should we make the outer relation, and which of them should we make the inner relation in order to take advantage of the index? Well, let's take a step back and think about the basic purpose of a nested loop join, specifically the inner loop. So this stuff here. Essentially, this stuff is a search. We want to look through S, search for something in S that matches that R. So it is a search, although an inefficient one, because we're just looking at potentially everything in S in a loop until we find the match. But we can think of this in more basic terms, kind of in more pseudocode. For every row in R, we want to somehow search through S for the row that matches that R. And searching is exactly what an index is good at. So instead of using a loop, we could use an index to do that search. But in order for an index to help, we have to have something to search for. So we still need these R's, and then we can search for those R's in the index in S. So we will want the index to be on the inside, and we still want to look at everything in the outer relation. So this is still a loop, and an index is not going to help there since we want to look at everything. So now it looks like this. We still have a loop on the outer relation R, but the inner relation is now a nested index lookup instead of a nested loop. So instead of something looking like n squared, it's going to look like n log n if the sizes of R and S were roughly the same. And there's just no getting around looking at everything in one of the tables, because we need to find every matching pair between the two tables. So we need to look at it, at least everything in one of them, so that we know what to search for in the other one. So the key is speeding up that search once we have something to search for. If we tried to do it like this, where we put the index in the outer relation R, it doesn't really work, because we need something to search for in order to be able to do an index lookup. So what do we search for? And we can't. So we would essentially have to turn this back into just a full nested loop. So you always want the index to be on the inner relation. So the performance is going to look like this. As we just saw, if the outer relation has the index, it doesn't help. So it's the same as it always was. And this is the worst case. If the inner relation has an index, then we still have to look at every page in the outer relation. That's still a loop. And then for each row in the outer relation, we do an index lookup. So each one of those index lookups is going to have roughly a cost log of the number of pages in S in the inner relation. So the difference between having the index in the right spot and not having the index in the right spot is essentially this factor right here, times total number of pages in S versus times log of the number of pages in S, which is going to make a huge difference. Log is a massive reduction. And even still, these are worst cases. In reality, it's not even really going to cost this much. It's not going to have to reload every page for every search through the index. It's likely going to be able to hold multiple pages in memory, and it's smart about the way that it caches them. So it's likely going to hold the root page of the index on S always in memory, since every lookup in S is going to have to start at the root. And maybe even the first couple of levels of that index are always going to be held in memory in order to avoid going to disk more than necessary. Now, what if both of the relations have an index? We can still only use one of them due to this issue right here. We need to we need to look at everything in one of the relations no matter what. So that just has to be a linear scan. So if both of the relations have an index, then which one should be outer and which one should be inner? And it comes down to this logarithmic term here. The big win that we're getting out of using an index is the logarithmic reduction. So we're going to get more advantage out of the logarithmic reduction on a bigger value. So we will want the bigger table to be used as S if both of them have an index. Now, just to kind of summarize the ideas behind the heuristics that the DBMS will use when deciding how to do a join. If there are no indexes on the joined columns, then it will use the smaller table as the inner relation. If there's an index on one table but not the other, then it will use the indexed table as the inner relation. If both of them have indexes that could work, then it will use the smaller one as the outer relation and the larger one as the inner relation. Now, finally, we've been looking at joins on just 2 tables, but what about joins on 3 or more tables? So something like A join B, join C, and then a condition on each of the joins. And it works about the same way, where the order that we specify the join in SQL doesn't matter. The DBMS is going to decide what order to actually do it in. And you can think of it the same way. It's a nested loop join, where if there are no indexes on any of them, then it's going to be a triply nested for loop. So it looks kind of like this. We have lots of options now. Instead of just which one's outer and which one is inner, we now have which one's outer, which one's middle, and which one is innermost. So we have a new kind of variable referring to whichever relation the DBMS picks as the innermost. And now S is the one that it picks as the middle. So we have R, S, and T. And lots of options for what to pick for R, S, and T. So how does it decide which one to pick? And sometimes its options are just limited by what columns are available in what tables. So as an example, let's say that A and C don't have any columns in common that are used to evaluate this where condition. So I couldn't be able to compare an A to a C if they don't have the information required in that where clause. So I couldn't put them as the first 2 relations like this. I couldn't have AC or CA, but I could have A then B then C, or C then B then A, or B first, as long as there's some way to link them together. And here's a little example just to make this more concrete. Let's say these are the 3 tables I'm joining, and just doing a natural join. So the condition for the join would be where titles.isbn equals inventory.isbn and inventory.serial equals checkedout.serial. So there is a way to link these 3 tables together, but if I start on titles, I can't go straight to checked out because there's nothing in common. I can't. Checked out doesn't have an ISBN or anything that I could use to compare for the join. Similarly, if I started on checked out, I could not go straight to titles. So if let's say I start on titles, then I have to go up through the inventory table first. So like titles would be R, inventory would be S, and checked out would be T. And I can compare the ISBNs, then I can take the serial and compare to checked out. Or similarly, if I started on checked out, I could go this way first and then down here. So checked out would be R, inventory would be S, and titles would be T. Those are not the only 2 possibilities, though. I can actually start on inventory. So I could make this R, and then let's say I go from here, I can go to either table because it has a column in common with both. So let's say I go to titles first. So titles is S. I match the ISBN of the first row up to one of the ISBNs in the titles table. So I now have a temporary row containing something from titles and something from inventory. So from here, I can go to checked out. Even though I'm going from titles to checked out, it's after already visiting inventory. So I have the serial number I need in order to compare to something in checked out. So I could do R, S, and T this way. Or I could do R on inventory, S on checked out, and T on titles. Here, though, is an example where we could do it in any order. If we did a natural join of these three tables, the column that we're looking for is card num in all three. So we could start with patrons and look for that card num in phones, or we could start with phones and look for it in checked out, or any possible permutation. So let's assume for now that all possible permutations are valid, and let's look at what the performance considerations are. So if it has all of these options, then how does it decide what order to use based on performance? And basically it follows the same principles, but with just a few extra details. So in the case where there are no indexes that will help with the join, it's going to put the smallest relation on the inside as T. And generally it goes in order, so R will be the largest, S will be the medium-sized table, and T will be the smallest. And I say generally because there are some special circumstances where it will make different decisions. That's usually, though, if all of the relations are quite small and memory considerations are not that relevant. If there is a considerable size difference between the tables, though, it will make the smallest one the innermost one. In the case where there is one index on one of the tables for the joined columns, then we want the indexed table to be either S or T, just not the outside relation. And it doesn't really matter too much whether it's S or T. Sometimes it can do an optimization where it can kind of short circuit the join condition if it's able to quickly find that S does not contain a match with R. So sometimes you might want the index to be S, but it depends on whether or not it can predict if it would be able to short circuit. And if there are indexes on all tables for all of the joined columns, then you would want the smallest table to be the outer relation. That's the one where you can't use an index anyway, even though it has one. For one of the relations, you at least have to loop through everything. So you'd want it to be the smallest one because you have to load every page out of that relation. And because you get a bigger win out of the logarithmic reduction on the bigger tables. And then as far as what to make S and what to make T, that again doesn't matter too much since they're both indexed lookups. So as long as there is some index on S that lets you find a match with the row from R, and some index on T that lets you find the match with the row from S, then you can use the indexes on the inner relations. Let me reiterate, though, these are not decisions that we have to make when writing SQL queries. These are decisions that the DBMS will automatically make for us.